Welcome back. In parts 1 and 2, we learned the universe is chunky and the electron teleport or quantum leap within the atom. But today, the universe is about to hand us a cosmic price tag. We think we can know everything about an object if we just look hard enough. But down in the quantum world, the universe refuses to be seen. You want answers? You've got to have to pay for them. Werner Heisenberg discovered a strict trade-off called the uncertainty principle. Imagine trying to photograph a glowing cheetah running in the dark, because why not? If you use a short exposure high-speed flash, you freeze the glowing cheetah. You know exactly where it is, but it's frozen. You have no idea how fast it's running. If you take a long exposure, you see a cheetah blur. You know the speed, but you can't point to a single spot and say it's right here. A little more specific, if you use a high energy photon with a short wavelength, it's like a foam-tipped arrow. You can get where because it can point to the exact spot where the electron is. But because the arrow is packed with energy, the moment it strikes the electron, it ricochets away. You found the location, but you just ruined the speed. On the other hand, if you use low energy light with a long wavelength, it's like trying to find the electron by throwing a big soft pillow at it. The pillow is fluffy and soft, so it doesn't move the electron, which means you keep the speed information but can't tell you exactly where the electron was when you hit it. You know the speed, but the where is in the blur. That is uncertainty principle. The universe keeps a balance of blurriness to protect its secrets. It's not a glitch, it's how reality works. Because of this blurriness, electrons don't act like solid marbles. They act like waves. And we actually prove this with the double slit experiment. If you fire paintballs at two slits in a wall, you get two straight lines of paint on the backboard. Simple. But if you fire electrons at those same two slits, they don't make two lines. They create a barcode-like interference pattern. For that pattern to exist, a single electron must travel through both slits at the same time, interfere with itself like a wave, and land on the board. It is in the state of maybe, or what scientists call superposition. But here is the creepy part. When scientists put a camera by the slits to see which hole the electron actually went through, the pattern disappeared. The electron saw the camera, got shy, and went back to acting like a boring solid marble. The act of looking forced the universe to stop being a wave of maybe and pick a side. Erwin Schrödinger, behind the Schrödinger equation for quantum mechanics, thought this looking rule was so ridiculous that he made up a famous joke involving a cat. But I want my cat alive and healthy, so this version is about a sleepy cat. Imagine a cat in an enclosed box with a quantum cookie. If the cookie stays whole, the cat stays awake. If it crumbles, the cat eats it and falls asleep. But because the cookie is quantum, it is in superposition. It is a whole and crumbled at the same time. Schrödinger argued that if the quantum rules are true, then as long as the box is closed, the cat must be awake and asleep at the same time. It only becomes one or the other when you open the box and force the universe to snap into a single reality. We call this snap the wave function collapse. We live in a universe of maybes that only become solid facts when the box is opened. It sounds like a headache, but these maybes are one of the most powerful tools in the history of science, because in the next video, we're going to stop looking into the box and start looking into a quantum computer.